Hello, geometry, and welcome to lesson 7.3, proving triangles similar. Again, I think to the geometry standard people, this is the most important section because we're going to do the 3 ways to prove triangles similar. Here we're going to kind of walk through transformation, through similarity transformations, why they work, and then the last part of this lesson is going to be actually applying them to problems, which I think is a little bit more important. Okay. So let's take a look at the first one. All right, so it says establish the angle-angle similarity theorem, right? This is going to be AA similarity. This is going to be one of our ways. So we want to say if angle A is congruent to angle R and angle B is congruent to angle S, is triangle ABC going to be similar to triangle RST? Let's explain. Okay, well, what we're going to do here is we're going to take triangle ABC and try to map it on to triangle RST. All right, so this is going to be done through a similarity transformation. So first step, we're going to rotate and translate. So you can see, right, that we need to rotate A, so it's down here in the bottom left, and R then B would then rotate so it's in the bottom right, so that A and B line up with the R and S. So we're going to rotate, right? Rotate it this way, and then translate it this way, right? So rotate, and we're going to translate triangle ABC so that A prime is equal to R. Okay, so when you rotate that, that means that R and A prime will be lined up. AB will be along side RS. So AB is about that far. So here's AB. Sure, there's B prime. And then C prime will be up here on RT. And these two angles will be congruent, and this will still be marked congruent to angle S. Okay, so that's step 1. So now how are we going to get B prime to line up with S? How are we going to get C prime to line up with T? So step 2 here, so now we're going to do our dilation. We're going to dilate triangle A prime, B prime, C prime with center A prime, so about the center, and scale factor. And we're going to use this side RS. RS over A prime, B prime. Again, we use RS because it's longer, A prime, B prime because they're corresponding. This is going to enlarge our triangle A prime, B prime, C prime. What this means is that angle A is going to be, or sorry, angle A prime is going to, double prime is going to be congruent to angle R. Angle B double prime will be congruent to angle S. And segment A double prime, B double prime will be congruent to segment RS. So this will now still be A double prime. It'll be congruent. B double prime will be over here now, right? It'll still be congruent. Here's what the triangle ends up. This will be C double prime. And there's our finished picture. And because we use the scale factor of RS over A prime, B prime, that means that this segment, A double prime, B double prime in blue, will be congruent to RS, which was the original long segment. And this is going to be angle, side, angle congruence. Once we dilated that red figure to make the blue, it lined up perfectly on top of the original black triangle and RST. And we have angle, side, angle. Therefore, triangle A double prime, B double prime, C double prime is actually congruent to triangle RST. And that is by angle, side, angle. And I know that the idea is that they're similar, but through a similarity transformation, you're able to make one figure go exactly on top of the other. You're able to get it to be congruent. So if you can get it to be congruent, that means that the original figures are similar to each other. So since we found a similarity transformation that maps triangle ABC onto triangle RST. Triangle ABC will be similar to triangle RST. And this right here establishes the angle-angle similarity case. The angle-angle similarity criterion for similar triangles. Okay, so here it is. So angle-angle similarity. Again, angle-angle with the squiggle, right? So we have two angles of one congruent to two angles of another, then the triangles are similar. So if angle A is congruent to angle D, angle B is congruent to angle E, then the triangles are similar. Okay, let's establish the next one. So the next one is going to be the side-side-side similarity theorem. Side-side-side similarity. Okay, so this is about proportionality. If Lm over PQ equals Mn over QR equals Ln over PR, is there a similarity transformation that maps triangle PQR to Lmn? So again, what this is saying is, are the three sides proportional? And this is also saying that the scale factors between the large sides and the small sides are equal, right? So that's the idea here, right? So we're just trying to prove, are these two triangles similar? So again, is there a similarity transformation that maps triangle PQR onto triangle LMN? Okay, so again, how do we do this? Well, first thing we're going to use is some rigid transformations, right? So if I look at this, P and L have to line up. So right now, I think P has to kind of flip up, R has to line up with N, and so R has to flip down, and Q is on the right side with M, so we don't want to rotate, but we do want to flip Q up. So this is going to involve a reflection. So this is where we're going to reflect and translate. Triangle PQR, so that we want P prime to equal L. So we're going to flip P up and then slide it so that P prime is where L is. And what that means is R is going to come down here and R is going to line up on LN. So that would be R prime. And Q is going to flip up and Q is going to line up on PM. And there will be the reflected and translated triangle. So now number 2, right? Now we're going to dilate. Now we have to make triangle P prime, Q prime, R prime bigger. So we're going to dilate triangle P prime, Q prime, R prime by, with center. With center P prime, with center P prime, and scale factor. And again, we're just going to pick one, right? With scale factor LM over P prime Q prime. So again, that's going to make this bigger, right? LM over P prime Q prime is going to extend this. So this will become P double prime. Q double prime is now where M is. And it's going to extend all the other sides the same way because all of the other, right here, right? LM and PQ, that ratio equals the other 3, so all the other ones are going to be extended the exact same way. So now R prime is down on N, R double prime, and now you have this big blue triangle, right? On top of the original black triangle LMN. So again, what this means is segment P double prime, Q double prime is going to be congruent to segment LM. And because the other ratios are the same, segment Q double prime, R double prime will be congruent to segment MN. And segment P double prime, R double prime is going to be congruent to segment LN. Therefore, triangle P double prime, Q double prime, R double prime is going to be congruent to triangle LMN. And we have created a similarity transformation to map one triangle onto the other. They are congruent by SSS. So this establishes the SSS similarity theorem. So since we found a similarity transformation, that maps triangle PQR onto triangle LMN, we know that triangle PQR is similar to triangle LMN. And again, this establishes the side case. Okay, so the next slide talks about the formal side similarity theorem. So here it is again SSS with a squiggle. If you have corresponding sides of two triangles that are proportional, right? So if the sides are proportional, such a big idea, not congruent, proportional. One set's smaller than the other. If they're proportional, then the triangles are similar. So again, sides are proportional. Sides proportional, not congruent. Right? There's a difference. Sides proportional, not congruent. This extended ratio is very, very, very important. Okay, last but not least, there's a angle side one as well. They do not make us walk through the proof of it, but here is what it says. It says for side angle side, which is SAS, if you have an angle of one triangle congruent to another. So one congruent angle, and then you have the sides that include that angle. The sides that include the angle are proportional. Then the triangles are similar. So again, in this picture here, it'd be AB and DE, so side, angle B and angle E, angle, and then BC and EF, side. Side, angle, side. Side, angle, side. Okay? And again, cannot emphasize enough, right? It's the two sides that make up the angle, and the sides are proportional. 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 Okay, so that's video 1. A lot of the background story. Sorry, it was a little bit longer. Video 2 is coming up with, I think, 4 good application problems.